This mic hot? Oh my gosh, we're on. All right. Hello, everybody. Woo! Welcome to RubyConf. I'm so happy to be the first person presenting to you here today. Actually, let's get going because I have 138 slides and only 29 minutes left. So let's move. Actually, all of you folks coming in from the back, don't worry, you're not late, you're just in time. This talk is called Some Assembly Required. Get it? Assembly, like, you gotta put stuff together, but also assembly is in the language, right? Yeah! My name is Patterson. I'm terribly out of practice from speaking since I haven't spoken in person for a while. I work for a company called Shopify, and I really enjoy working for this company. And I think you would too. And one of the reasons I really like working here is because we get to, they actually pay us to talk shop. All right, thank you. Yes, I'm known as TenderJIT Online. If you don't recognize me, this is my icon on the internet. I decided to dress like that today so you'd more easily be able to recognize me. I am on the Ruby core team and also the Rails core team, and I am extremely happy to be here. I am so happy to be seeing all of you in 3 dimensions and HD. So I'm really happy to be here. And also, those of you those of you watching on the live stream, I actually have my iPad set up here with the Discord open. So if you type some stuff in there, I'll probably see it. I love local stuff. Like anytime I go somewhere different, I try different local things. So last night I had some Coors Banquet. Because it's a local beer, so I was excited about that. Also, I went to lunch the other day with a couple friends, and we sat down and I asked the waitress, like, what is local here? And she thought I meant like local, like what do we source local, but I mean like local specialties. And anyway, I was reading the menu and one thing caught my eye, which was chili Colorado, and I'm like, oh wow, it's got Colorado in the name, so this must be local. And then she took the order, and as they were preparing the food, I decided to Google it because I was like, well, let's read about the history of chili Colorado. This must have a rich history here in the state of Colorado. And it turns out it is a traditional Mexican dish, not chili from the state of Colorado. It just means that it's red. And this really confused me because I feel like that's the default color. Like if you say chili, it just means red in my head. So I was kind of disappointed. Anyway, if you have recommendations for local things that I should try, please let me know. I would be happy to try them. I'm going to talk to you a little bit today about a project I've been working on called TenderJIT. A little bit. You'll find the repository here on the link. It is a JIT for Ruby that is written in Ruby. And actually, it's not the first JIT for Ruby that's written in Ruby. There's a couple other ones that I kind of want to mention. First is one of the predecessors here is Rhizome by Chris Seaton. He's one of my colleagues. It's not really designed to be used as a JIT per se, but show you how JITs are supposed to work so you can understand how to build a JIT. The other one, which I think is really interesting, is this one called the Ludicrous JIT compiler, which Chris told me about this JIT project, and it's about 12 years old. So this is probably the first JIT for Ruby that was written in Ruby, though it does have a C dependency, and TenderJIT does not. So TenderJIT's goals are, I'm not going to talk about TenderJIT the whole time, but I want to tell you a little bit about the goals of the project. First off is to be fun. I think it is a fun project, so I will check that goal off. Not to toot my own horn, but I enjoy the code that I write until I revisit it a few years later, and then I'm like, this is awful. The other goal is to be written in pure Ruby, so I want something that's written in pure Ruby. It is currently written in pure Ruby. I also want it to be installable as a gem, which it is not installable as a gem right now, but it will be at some point in the future. And the final goal is to speed stuff up. Maybe this isn't necessarily a hard and fast goal. So why did I write this thing, or why was I working on this project? I mainly started this project essentially as a learning tool So my team at work, we're working on a project called YJIT, and you should go see Maxime's presentation later on in the conference to learn more about that JIT compiler. And to be honest, like I didn't feel super comfortable working on this JIT compiler because I'm not really a JIT expert necessarily. Yeah, so I said we're working on YJIT, and I wanted to make myself more like level up my skills so that I could be better at my job, basically. And I wanted a low stress place where I could practice and check stuff out. And the other reason I did this was just to like see if I could. Sorry, Richard, there's no IKEA in this talk. I wanted to see if I could build this thing. So for me, like programming is a really creative and fun endeavor. Like I love to program. And many times I'll just write a project just to see if I can do it. And this is one of those cases. So I think maybe people are asking, does this thing actually work? And here's some sample code to show you, like, it doesn't actually compile stuff automatically itself yet. Like you have to specifically say like, hey, please go compile this thing, and it'll go compile it. But if we run this and compare the JITted version versus the interpreter or the YARV version, you'll see that the speed is actually better. Like the base case takes about 10 seconds to run, whereas the TenderJIT JIT compiler will take about 4 seconds or so. And of course, like people are probably asking, well, how does this compare to a real JIT compiler like YJIT? So I benchmarked that too. And if we run that with --YJIT, you'll see that it's half the speed of TenderJIT. So maybe TenderJIT is not that fast. But I think this can be fixed in the future because actually the design of my JIT compiler is basically 90% borrowed from YJIT. So I think that like basically in the future the top speed can probably match that of YJIT. Anyway, TenderJIT isn't why I'm here. What I really want to talk about is building a JIT compiler from nothing and doing it in pure Ruby. And what I hope is that by the end of this presentation, you'll be able to build your own TenderJIT, or if not, like at least contribute to TenderJIT or even contribute to YJIT since the design is very similar. So the first question I want to answer though is like, what is a JIT? And to me, a JIT is something that emits machine code at runtime. And then you have to ask like, okay, well, what is machine code? And I think this is a very interesting question. To me, machine code is just a sequence of bytes. So you have a sequence of bytes, and the CPU interprets that. And I really want to emphasize this. Machine code is just a sequence of bytes. So any language that's capable of putting together a sequence of bytes is also capable of producing a JIT compiler. So I think maybe in the future it might be kind of fun to do that with, say, like SQL. Like maybe we'll write a JIT compiler in SQL, or even possibly we'll write one in PostScript. Like I think that would be fun. I've always had in the back of my mind, like I always see these printers that are sitting around offices. When I went to an office, we'd see these printers and they're just sitting there doing nothing. What if we could take them and turn them all into Bitcoin miners? You know, all be rich, right? Anyway. So we can actually assemble, like we can put together sequences of binary data in Ruby. That's not a problem. So here's an example of doing that. We have a string. We just do print on the string. And actually, if we pipe the sequence of bytes to a disassembler, we'll see that in fact, yeah, that's machine code right there. It does something. So I'm sorry. The Discord is quite funny. I should not read this. So we actually have machine code output here, and we're doing it at runtime. So does that mean that we wrote a JIT? Maybe. Well, what we're going to be doing today is we're going to be writing a template, what's called a template compiler. And a template compiler is exactly what it says. It's just a template, like a template compiler. It's a compiler that uses templates. And I don't mean this in any kind of like computer science jargon way. I mean this is like really a template. For example, like you think about a Rails application where you have an ERB template where much of the HTML is just static HTML, but you have some sections that are dynamic, and you insert dynamic values into those. We're basically doing the same thing, but instead of building up an HTML page, we're going to be doing this with machine code. So let's build a JIT. We're going to build an actual JIT, like a real one. This is going to be a legit JIT. And we need to use source control for this. So this is going to be a legit JIT that is stored in Git. Okay, no laughs. All right, fine. If we refactor this sentence a little bit, then we can factor out the JIT. We're repeating that here. So we've actually got 2 legits here in Git. Am I too old for this audience? Like, is that? Thank you. So we're going to build. In order to build a JIT, I think we need basically 2 things. The first one is a way to generate machine code. We need to be able to generate machine code at runtime. And the other thing that we need is we need a way to translate our Ruby code into machine code. And in order to do this, we need to understand, we need to have some kind of translation process. We need to understand what we're translating from and translating to. So I want to talk a little bit about the different machines that we're dealing with. We're dealing with YARV, which stands for yet another Ruby VM, and that is the virtual machine that backs your Ruby program. So we have one virtual machine there. And then we have another processor, which is your actual CPU. So we have a virtual machine and a real machine. And we need to be able to translate from one machine to another. And in order to do that, we need to understand the differences between these 2 machines. So I'm going to talk a little bit about what YARV is versus what the CPU is. YARV is what we call a stack machine. It's a stack-based virtual machine. And here's an example of a stack-based machine. Say we have some sample code here, like 5 plus 3. Maybe the compiler compiles that into these 3 instructions: a push 5, push 3, and then a plus. And we have a stack here, a machine stack on the right. Now, when the virtual machine executes this, first we'll call push. It'll push 5 onto the stack. Then we'll call push 3. It'll push 3 onto the stack. And then the plus instruction will actually pop 2 values off of the stack, compute the addition, and then push the addition back onto the stack. Just so we have some, this is the intro to Ruby Internals, so let's talk about some words here. So we have some good vocabulary for talking about this stuff. This arrow right here that points at the instructions, this thing is called a PC. It's a program counter. It keeps track of what we're executing right now. This other arrow right here, this is the stack pointer, or SP, and it keeps track of where the top of the stack is. Actually, in Ruby, we're always pointing at the next place we're going to write to, which is why that box is empty. Now, we can see these YARV instructions. So this machine code that I put up here, or this virtual machine code that I put up here on the slide, this isn't actually YARV code or YARV byte code, but we can see the real YARV byte code. So here's an example of looking at real YARV byte code. We have a sample program that's just 5 plus 3, just like we looked at. And we can call Ruby with --dump, and it'll dump out the instructions for that program. So you can see it's very similar to the fake instructions that I showed a little bit earlier. What's really, really nice about these stack machines is we don't have to keep track of where to store stuff or where temporary variables go. We can kind of treat this as if we have an infinite stack depth. It might not actually be infinite, but we can believe that it's infinite. So for example, here we have a function that we call foo, and we pass in a whole bunch of different values to foo. And actually, by the time we call foo, our stack is now 7 deep. And what's really nice is we don't need to really think about where this temporary storage goes. So the next thing to look at is a CPU, which is a register machine. Now, the register machine works a little bit differently than a stack machine does, in that it just has a limited number of registers that we can deal with. It also has a stack, but we're mainly trying to deal with registers in the CPU. So rather than storing the values in the stack, we'll store temporary values in registers and manipulate those registers. So here's a sample program again, 5 plus 3. In the middle, we have the machine code, and on the right-hand side, I put a chart which is the values for the register for each register inside of the machine. So right now we're only dealing with 2 different registers, and the way this code executes is we say, okay, first we're going to copy, mav means copy, we're just going to copy the value 5 into the register R1. So when that happens, we get 5 into the R1 register. Then we're going to copy the value 3 into the register R2. So now we have 5 and 3. And then we're going to say add, and we want you to add R1 and R2 together. And in this syntax of assembly language, what happens is we'll add the two values. So R1 will be added to R2, but R1 will be clobbered and we'll have the result of that addition. So R1 will contain 8. And you'll notice that R2 didn't get cleared, and I did that on purpose, and that's because the CPU doesn't clear it. The value is it just stays there unless you change the value. So we can see, like, we looked at real instructions with YARV. Let's look at real instructions with the X86 machine code. So I wrote a C program here that was as close to my sample. Like, I did my best to generate the same machine code as the stuff I put in the previous slide. But here it is. We say, you can see right here, we copy 5. In this case, we're actually copying it into the stack, but don't worry about it. It's fine. We don't need to think about it. Then we'll copy 3 again into the stack, and then we'll say, for some reason, we do another copy. We copy from the stack into the EAX register right here. So the value 5 will end up in EAX. And finally, we'll add from the stack into EAX, and we'll end up with 8 inside of the EAX register. So the next thing we need to do is we need to generate machine code. Now that we have an idea of the two different types of machines that we're dealing with, we need to convert one into the other. And to do this, we need a way to actually generate that machine code. So I wrote an X86 assembler called Fisk, and you can go check it out here on my GitHub page. It lets you write assembly and put it together at runtime. And here's an example of it. In this case, where, like, on the left-hand side is the Fisk Ruby code that we write, and on the right-hand side is the disassembled output of it. So you can see here we're writing from 5 to R9. That's on the left is the Ruby code, and on the right is the machine code. And again here, 3 into racks. Then we say add R9 with racks, and finally we do a return. And actually, Fisk has an eval-based API. So if we want this to look like very, very similar to the machine code, we can do this. This is the same program. But you can see here it's quite similar to the machine code that we output today. And like, now that we're assembling machine code at runtime, like, did we build a JIT again? I think we did. Oh yes, this is number 2. So now that we have this machine code, we need to be able to actually run these bytes. Like, it's cool that we put it together and we can disassemble it, but it's not doing anything. We would like it to run, which would be great. So in order to get this to run, we need to somehow point the CPU at those bytes. And Fisk actually comes with a helper to let you do that. So here's an example of using the helper. It's essentially the same program. Here we write out our assembly code. Next, we allocate some executable memory. This is memory that we can point the CPU at, and the CPU will execute what's in that memory. Then we ask Fisk, like, please write all of the bytes out to that executable memory. And then finally, we can say, hey, we call the toFunction method. The toFunction method returns a lambda to us that we can actually call, and we'll print the return value of that. And when we do that, we'll see the output is 8. We were able to actually write machine code into executable memory and then execute it. And what's kind of cool is, since this toFunction thing actually just returns a lambda, we can pass that into define method, and we can say, okay, well, I just want to define a method called add, and it'll do it. So we can call add, and we get 8 out of there. So now, did we do a JIT? I think we did. I really think we did. Yes, we did a JIT. Come on, please. Please. In pure Ruby, we did a JIT. Now I have to admit though, like, let's take a look at this pure Ruby. I think we got to put this pure Ruby in quotes here, because if you look at this, yes, technically this is indeed Ruby code. We wrote Ruby code, and this Ruby code was turned into machine code, but it sure looks a lot like machine code that we're writing. I don't really want to put this inside of my Rails controllers. I feel like we might come across some kind of maintainability issue. So what we'd really like to do is we'd like to have some kind of automatic conversion. We'd like to just write this method, 5 + 3, and then have it somehow automatically translated into this machine code here. We need a way to convert the YARV code into x86. We need to write a YARV to x86 converter, and that's what we're going to do now with the 10 remaining minutes that we have, hopefully. If I can get this done on time, it'll be just in time. If I keep making really awesome jokes, it will not be done in time. All right, so it's pretty easy for us to like dump the instructions. So we can call Ruby with --insns or -dump this command up here and see the instructions, but we can't programmatically access them that way. It's just, we're just viewing them on the terminal. But there is this class here, Ruby VM instruction sequence, and we're able, with this class, we can get programmatic access to the instructions for any particular method. So we can say, hey, I want to access the instructions for this add method. And we can print out, we can say like .2a on the object, and it'll print out an array, and on the right-hand side is the output. And the stuff we really care about that we've been looking at is down here in the bottom right, this put object, these two put objects, and the opt plus and the leave. Those are the things we've been looking at. And with these instructions, we can actually turn around and write our own little mini YARV. So we can write our own interpreter for these instructions. So here's a mini YARV that I wrote. Our mini YARV has a case statement for each of the different instructions that we're going to deal with. So it has a put object and an opt plus and a leave. And each of these blocks manipulates a stack. Remember we said that Ruby's virtual machine is a stack-based virtual machine. So we've written our own stack. So we're just using an array in this case. So we'll push onto the array and pop off the array. And I also put in little prints there so we can see what the virtual machine is actually doing. If we run this code, we'll see, okay, we pushed on 5, we pushed on 3, we popped off 5 and 3, then we pushed on 8, and we finally returned 8. Now, we want to be able to convert this into machine code that the CPU can actually execute. And the secret to doing that is this stack object right here. Recall that the Ruby virtual machine is a stack-based virtual machine. The CPU is a register-based machine. And we need to be able to convert between these two these two types of machines. In order to do that, we'll create something called like essentially a virtual stack. This virtual stack object, all it's going to do is translate from this stack-based management into a register-based management. It just maps registers to positions in the stack. That's all it does. So here's a sample virtual stack. This virtual stack only has a maximum depth of 2. I just wanted to call that out. It's only managing 2 registers, the R9 register and the R10 register. And the interface for this particular class is anytime we want to push something onto the stack, we call push. And push will return the value or the location where we need to write. So pushing onto the stack doesn't actually write anything. It just returns to you the area where you need to put the value. And when you pop, it doesn't write anything or do anything. It just tells you where you need to read that value. So using this interface, we can integrate that with our virtual machine here, and we can say, hey, when I want to push onto the stack, we'll call push. And notice I put these write calls in here. There's a call to write. It doesn't do anything right now. We're going to fill out in a little later. When we call push, it tells us where should I write. When I call pop, it says that's telling us where should we read. And again, when we do the add, we need to push again. So we say, okay, stack.push, and then we write to that particular location. And again, when we leave, when we're returning from the function, we say, I'm going to pop off the stack and read from that location. So now we can integrate Fisk to actually generate these X86 instructions. We say right here, okay, we've pushed onto the stack. We'll write the value to the stack, to the quote stack, our virtual stack. And again, we can add the 2 values here that we've popped off, and then we'll write to the virtual stack again. And then when we return, we'll read from the virtual stack and write to a special return location. And down here at the bottom, we're just going to print out the machine code that we generated. And if we print that out here, we'll see here's the machine code that we generated on the right. And I want to step through that along with the CPU state in our Ruby code. So the normal Ruby code, the virtual machine, is going to say, okay, we're going to push 5. And in our case, with the machine code, a push means we're just going to write to the R9 register. So we write 5 there. Then when we push 3, we're just going to write 3 to the R10 register. Then when we execute add, we're going to add R10 and R9, and then we're going to push R10 onto the R9 register. So we have to do a push there. You'll see down here with the CPU state, like what the values of the register are at each moment. And then finally, we have to copy the value to the top of the return value to the racks register and then return. Okay, now we can actually refactor this code, this compiler, into a generic method that just takes a method. We say, hey, I want you to compile some particular method. So we'll do that right here. Oh my God, 5 minutes? Okay, let's move more quickly. We'll turn this into a function since it returns a callable, and indeed we can call the fast add method and we'll get 8 and 8. So we have two methods here. We have finally been able to take Ruby, which gets converted into YARV, and then we were able to convert that YARV into X86 instructions. So we can perform some optimizations on this. Actually, let's do a couple optimizations extremely quickly. When we do this add, we notice that we have to do this copy here. We're moving R9 into R10, and then when we do the add, R9 gets added with R10, and the value is dropped into R10. And when we do the push again, we have to copy the value from R10 into R9. So we know that we want the value to end up in R9. So it would be nice if we could just swap the two values in add. So instead of saying add R10, R9, we could say add R9, R10. So if we did that, we would be able to reduce by one instruction. And we can actually do that because we know that A plus B equals B plus A, so we can swap those two. So if we do that, we're able to eliminate one move, or one copy. So we got rid of one instruction here. And the only important thing we need to point out is that down here, when we're processing this opt-add instruction, we still need to push onto the stack just to keep bookkeeping. We don't need to do anything. We don't need to write anywhere. We just need to push so that we have correct bookkeeping. The other optimization I want to do is when we return from a function, we know the stack depth is always 1. So we have one thing on the stack, we return that. As you all know, in Ruby, we have an implicit return value. Every function always returns something, so there will always be one thing on the stack to return. We know that that last value has to be inside of the racks register, so we'll change our virtual stack to say, okay, we're just going to manage racks and R9. And if we do that, then when we plug this virtual stack into our compiler, the return value will actually automatically end up in racks for us. And then when we return from the function, we just pop off the stack, but we don't need to do anything, and we're able to eliminate yet another instruction. And of course, there are other optimizations we could do. We know it's a 5 plus 3 literal, so we don't actually need to do these adds. We can just return an 8, et cetera, et cetera, et cetera. I just wanted to show this because I thought it was fun. So did we do a JIT? I think so, yes! Yes! We did a JIT! Okay. Oh my God, 2 minutes. I'm about to, I was very close to an F-bomb there. I did not do it. Okay, so one thing that sucks about this is we have to define a new method. We're creating a new function, defining a new method, and MJIT and YJIT don't do that. We don't want to do that. So in order to figure out how they do that, let's dive a little bit into how the virtual machine works. Here is a virtual machine entry point VM exec, and I just want to point out one if statement inside of here, this if statement. It calls MJIT exec, and if we go read MJIT exec, actually I want to point out, if MJIT exec returns QUndef, it'll go through the normal VM process. So MJIT exec is our hook point for the JIT to execute something. If we go read MJIT exec, it's way too long, we're not going to read it, and it's also in C. I have translated it to Ruby, and this is what it looks like. MJIT exec gets an EC, the EC points at a CFP, the CFP points at an IC, and the IC points at a body. Yeah! And here we keep track of the number of calls that we've made, and if we've made enough calls, yeah, I pointed that out, okay. If we made enough calls, then we'll actually compile the instruction, or the instruction sequence, and down here at the bottom, you'll see if we have a JIT function, we're going to call the JIT function. So the compilation process is responsible for defining that particular JIT function on the body. You don't need to understand this too much, just that the JIT contract is write a C function to JIT func and I'll call it. That is the contract. And I think I threw a bunch of acronyms at you, especially up here, so I want to explain those a little bit because this is intro to Ruby internals. EC stands for execution context. There is only one. This is like the global state of the VM. This is like just global values we need to know about. The EC points at the CFP. CFP stands for control frame pointer. That represents the actual stack frame, the thing that you're executing. So in this case here, we have a recursive function. Each time we recurse in that function, we'll push the stack frame on, and that stack frame points at the previous one. And the EC, the execution context, always points at the top frame. So as we're recursing through here, we keep pushing these frames onto the stack. Now these CFPs, again, I said they point at an ISEQ, which we know stands for instruction sequence. They're just pointing at the instruction sequence that they're currently executing. There is one instruction sequence per executable code. So for example, there is an iseq for this method, there's an iseq for a block, there's iseqs for your files because the whole file will execute. And in this case, they're all pointing at the same one because it's the same function. Now the iseq points at a body, the body is just stuff. It's just like stuff. There's various things in there. But the important thing is that inside of that is the JIT func, and that's the thing that we need to write to. We don't need to worry about most of this graph. We just need to worry about these two particular things because we actually have access to this iseq object via the instruction sequence object. But we're one hop away from the body. I'm out of time. Let's do this. We can do this. So how do we get to that body? I have a solution for you, which is two different classes, which is, I feel that this information might be a tad bit illegal. Don't use this in production. Or do use it. I don't know. So here's the first class. This class is inside the fiddle library, and this class will, given an address, read memory at that address. So here's an example. We'll say, I want to read, I'm going to point you at the address 123, and I'm going to read the first byte. And we can give it a range, and we can say, hey, I want to read a bunch of bytes, or we can give it another range. We can write to the bytes there. The other tool to use is fiddle DL on DL wrap, which returns the address of a Ruby object. So given a Ruby object, it'll give you back the address of that Ruby object. So let's do something really super fun with this. Let's say we have a string that is frozen. Of course, you all know if you try to write to this frozen string, you'll get an exception, but we're not going to let that stop us. I mean, we're programmers, right? We can do whatever we want. So we're just going to say fiddle.dl wrap. We get the address of that string back. We're going to create a new pointer. That pointer points at the memory for that particular string object. And we're going to say at 16 bytes in, we're going to write E. And you can see down here at the bottom, we've mutated the string so it says E-L-L-O. So now we've mutated a frozen string. Oh yeah, I had arrows. Okay, yes, great. Good for me. Nice. Nice, yes. All right, so let's say, I'm not going to explain this particular slide, but it's something that you could write if you were so inclined to write this. But I have to posit a question to all of you. What if this were a gem? What if it were a gem? Actually, I was preparing these slides, and I get, like, when I'm preparing a presentation, I get super duper productive on everything besides the presentation. So I wrote this gem. All right, anyway, so we need to write to memory, but the question is, how do we know where to write to memory? And there is a tool that knows this. Like, if you ever debugged a C program, you'll know that GDB and LDB are able to deconstruct a struct and show you where all of the information is, or what all the members of that struct are. And in fact, this comes from what's called dwarf data. This is debugging information. It's just text, and we can actually process this text. So I wrote a Ruby program to process this text. It's called OdinFlex, and this thing will give you the layout of memory, like the layout of any struct. So we can say, like, okay, we've got this really cool method here. We got cool method. We get an iseq object for the cool method. This instruction sequence object is actually an instance of an RData, which is on the right-hand side there. So we have an RData structure. OdinFlex provided this RData class here, and it allows us to access the data member of that. So we're able to get that data member. Down here, we're going to create a new RB-iseq-t instance. So this is essentially accessing, it's telling the program, hey, this is a layout of RB-iseq-t. And you'll see down here, we access the body, which is the constant body, and then we call .jit func, and that is our JIT function. And in this case, we'll return 0 because there is no JIT function. We haven't assembled one yet. So we'll assemble one here that just returns the value 42, and we'll assign that to the JIT function down at the bottom. And if we execute this program with the normal Ruby, cool method will return 1, 2, 3, 4. But if we call with --JIT, it'll return 42, and that's because we assigned a JIT function there. So, thank you, yes. Oh my gosh. So we have a pure Ruby JIT here in 3 different parts. I'm going to wrap this up now. It took 3 different parts to define a pure Ruby JIT. First, we needed the Ruby VM instruction sequence in order to access the different VM instructions. Second, we needed a way to convert those instructions into X86, and we did that using Fisk. Third, we needed a way to write this JIT function out to the internal data structures of Ruby, and we were able to do that with OdinFlex and Fiddle. So those are all the components of TenderJIT right there. So you should be able to write your own today. Yeah? Yeah? Yes? So I want to review some of the projects first. There is a Fisk, which I think is a low stress way to mess with x86 64. So go there if you just want to do some assembly. TenderJIT, of course, please come contribute to the project, please. It is a JIT for Ruby that is written in Ruby. Also, if you study this, you'll know the architecture for YJIT, so you can work on a real, like a good JIT, which is a YJIT. And I wasn't sure what link to put in here because we've merged this into Ruby now. So you can contribute upstream or come to the Shopify Ruby fork and we'll definitely help you there. Again, I want to say thank you to Shopify for employing me. Also, we are hiring. Thank you to the organizers of RubyConf, and thank you all of you for coming here in person and seeing me here today. It was good to see you in 3D. Thank you.